Okay, so this is, the title is a mouthful, I won't say anything about it. And this is work done by Thibaut de Piré, who was a postdoc at Technion with Yariv Kafri, and you can read about it in this paper. I'll give you, the outline is, I'll first tell you about the problem that started this, which is not our work, and then what happens when you introduce fluid, and physics of marginal operators and anomalous exponents, and I'll summarize. This is better. So, if you have an object in a medium containing a bunch of particles, and you describe that object basically by a potential that acts on the particles, then if the particles were at thermal equilibrium, all you will get is e to the minus beta v for the distribution of the particles. On the other hand, if the particles are self-propelled, then the story turns out to be completely different. And what happens is that basically, if this object has a vectorial shape, if these particles are active, they'll start ratcheting around this obstacle. As a result, you'll have a sort of source of force. And if you look at the dynamics of these particles, at the concentration of these particles, they'll, on long time scales, of course, they'll have an effective diffusivity, but the steady-state distribution of the density will be determined by this object acting like a force source there, and you will end up getting a power law tail, which I guess must be on the next slide. Yeah. So what you'll end up getting is that the degree to which that obstacle is forcing the active medium is given essentially by the effective force that the inclusion exerts on the active particles, which at thermal equilibrium would be 0, right? And so you end up getting a 1 over r squared in 3 dimensions decay of the density. So you have an obstacle, you have these active particles running around, and rather than being obligingly distributed just as e to the minus beta v, you have a very, very long power law tail. So this is what these guys showed several years ago in a very beautiful paper. The fact that you have these long-range effects has all kinds of consequences. For example, if you have two such obstacles, they talk to each other at long distances. Even more dramatically, if you have a system which in bulk wants to phase separate, disorder at the boundary can actually change the bulk phase diagram. So that's the background. So now the question is, if instead of a collection of sort of active Brownian or active run and tumble particles, you actually have active particles in a fluid, what changes? Okay. So if you have a fluid, essentially with a little bit of work, you can show that what will happen is that the same active particle density field will now, in addition, be advected by the hydrodynamic velocity field. So the idea is this. You've got this inclusion, you've got these active particles, each of them is a swimmer, each of them is a force dipole, it's creating flows. So you'll now, as a result, have flows around this object, non-trivial flows at the scale of this object, and those flows will advect the active particle density, and the question is there a qualitative change in the density distribution, in the density profile, or is there not? Okay? Now, the important case is when this inclusion has overall a vectorial shape. If you take, in an active medium, if you plunge into it an obstacle with a vectorial shape, then, and it's a fluid, this vectorially shaped object will itself become a swimmer. So if you want to hold it in place, you have to grab hold of it with a force. So you have to introduce an external force into the problem. In other words, the far field velocity around an inclusion, a vectorial inclusion held in place, is actually the velocity field of a force monopole. So it's a 1 over r. Okay? So now what you have, therefore, is that you will have a sort of local structural characterizer of the inclusion. You'll have a velocity field that's 1 over r at long distances. And so now if you look at these two terms, you can ask, if I let r go to br, and I compare these two terms, if this velocity field is the 1 over r squared of a force dipole, then this will scale down more under r going to br than this term. And therefore, you can forget about this guy at large distances. For the case of a vector obstacle, because it's a 1 over r, these two guys scale exactly the same way. So advection is marginal. Okay? And then the question is, what happens? So the problem you have to solve is to work out the density field for a velocity field generated by the Stokes equation of a bunch of swimmers with an obstacle in place. Okay, you have a little source here due to the inclusion, which is some little vector c characterizing the inclusion times, far away from the inclusion, this thing is all localized there, so you can think of it as the gradient of a delta function dotted into the little vector c that characterizes the inclusion. And there's a fairly elaborate calculation, but the really big surprise is the following. You might think that you look at this, you should be able to guess the form of the far field density just by power counting. It turns out, by stupid power counting, you cannot. The kind of dimensional analysis you end up having to do is to conjecture that the density is a 1 over r squared times something characterizing the strength of the inclusion times some function of theta and phi, and you have to include an inner scale, a small length scale L, associated with the inclusion. In other words, your dimensional analysis can't just use the position coordinate, you have to introduce anomalous scaling. If you don't do this, you get an answer that diverges, okay? So you have to solve for this density field, you expand it and so forth. You must allow for the decay to have an anomalous piece, meaning, anytime you do dimensional analysis and you want to get the naive answer, you have to have another length scale in your hand. That other length scale is the small scale associated with the obstacle. There's exponents epsilon m associated with each azimuthal harmonic component. If you try to do this by setting epsilon m to 0, this function blows up somewhere in angle space, okay? You can do a fairly elaborate perturbative calculation, perturbative in the non-dimensional strength of the force characterizing the inclusion. And what you find is the decay, remember, epsilon m is the degree to which the decay deviates from 1 over r squared. It's 1 over r to the 2 plus epsilon m, m being the m spherical harmonic index. And what you get is that for m equals 0, this epsilon is 1/3 lambda squared, where lambda is this guy. And m equals plus and minus 1, for example, it's minus a 12th lambda squared. This will apply when the obstacle is not axisymmetric. Only this will apply when the obstacle is axisymmetric. There's a non-trivial angle dependence, theta dependence, which also involves the same non-dimensional, this Peclet number of the forcing. Okay? And so what you have, therefore, is, I guess I've actually talked so fast that I've used less than 8 minutes. I guess I have. Okay. So I'll come to the conclusion, but meanwhile, you can also now imagine two such inclusions, hold them in place, let them turn freely, and you can work out the flows they generate and the dynamics that arises, which is quite nice. So I'll close by summarizing. Basically, a polar vector-shaped inclusion in an active suspension brings in the physics of marginality. The density field decays as 1 over r squared plus 1 over r to an exponent 2 plus something. That plus, the something can be positive or negative. The decay of the density away from axisymmetric inclusions is faster than 1 over r squared. Around non-axisymmetric is slower than 1 over r squared. The decay exponent depends continuously on a non-dimensional characterizer of the force associated with the inclusion. So what this means basically is this. Imagine you're a Stokesian swimmer and there is some obstacle somewhere in a fluid, some island far away. It's like by measuring the concentration field of the other swimmers around you and how that varies with distance, you can kind of tell something about the shape of their inclusion very, very far away. Because the decay exponent depends quantitatively on the vectorial asymmetry of their object, which is pretty weird. I have no idea if an organism can use this or if we can use this in any way. And there's fun dynamics with pairs of these inclusions. Anyway, this is really, the brilliance of Thibaut de Pirret that's responsible for this work, but Yari and I, to some extent, contributed to it. And you can read about it there. Thank you.
Questions?
Yes, sir. Vijay.
Inclusion fixed in a position, but if you let it flow around.
If you let, then it will swim around, and then you go back to 1 over r squared for the density.
So does that affect the density distribution?
No, I'm saying the density, the power law of the decay of the density with distance from it will be the same as for dry. If you want this dramatic deviation from the dry case, the inclusion has to be vectorial, and therefore, in which case you will need to hold it in place. And then the density profile is governed by the strength of the inclusion, the strength of the sort of force required to hold it in place in this rather interesting way. And yes.
So probably you mentioned this, I missed it, but the inclusion is free to rotate. If it's like a rod-like inclusion I'm thinking of, then you're holding it fixed in a position, but you're
correct, yeah.
allowing it to
change
its orientation. Yeah. Like if there is local rotation, you're allowing it.
So, but if it's not chiral, it won't rotate on the average.
I see.
But of course, the moment you have two of them, then they'll start doing all kinds of fun stuff like I showed you at the end. Is the size of inclusion? The size is crucial. Remember that little length scale I told you? The only way you can get a departure from naive dimension analysis is if there's another length scale in the problem. That length scale is a small scale associated with inclusion, roughly its size.
So let's thank the speaker once again.